All right, so today, as we talked about yesterday, for the confidence intervals, again, the idea is I don't know something about whatever it is. Okay, now we're going to do it for means or averages, of course, initially. That's initially what we're going to do. And then we're going to look at some other things too. So I'm just going to talk about it in general today with, we talked about this yesterday in class, but we could do this with any number of things. But again, we don't know something about the average. We don't know something about the standard deviation. We don't know something about what proportion of people like strawberry ice cream, whatever it happens to be. So what do? We always take a sample. Okay? Always take a sample. How big? Well, size n, right? So 100 people, 150 people, whatever it happens to be. Okay? Obviously, bigger is better to a point, because obviously the more there are, the less variable it is. Meaning the smaller the standard deviation is. And so we talked about this in class yesterday, that you could write it like this for the averages. By the way, this could be sigma or it could be Sx. That is the standard deviation of the sample. Sample deviation. Oftentimes we won't know sigma. This is the population deviation. If I know it, cool. But most likely I have no idea what it is. Okay, so in practice, we typically use Sx. Okay, but either way, there it is. And then less than the mean. And then, now what does this really mean to me? Well, what it really means is this. I don't know this guy. So I throw a dart, and it lands here somewhere. That's where X bar is, yes? And then I'm going to go this far over this way. I'm going to go over Z standard deviations. Are you with me? This is the standard deviation. I'm going to go that far on this side, and I'm going to go that far on this side. Well, the same distance on this side. You with me? Z standard deviations. Except for this one, of course, negative Z, because we went below. Make sense? This right here is what is referred to as the margin of error. The margin of error. And what the trick would be is I want the smallest margin of error I can get my hands on. Okay, whatever. So, again, that's the idea. And we talked about that yesterday, and that will always be where we're starting from. Now, normally, a lot of times I will actually write it in this fashion. And so what I will do is I will find the margin of error first, and then I will either add it and then subtract it to find my actual interval. Okay, that's how I do. That's how I'm going to model it. That's how it's going to be true. The only difference between standard deviations and averages, different distribution, obviously. And we're going to be concerned we don't know this guy, so we're taking a standard, so we just won't know him, right? So what do? You take a sample and you find this guy, right? And you build a confidence interval around him, okay? And ditto if we find for proportions, okay? So that's the game. That's what we're going to be doing 100% all the way through. Now, we mentioned this, I think, yesterday. Again, I'm filming this in the past, filming this a long time ago, before yesterday, if that makes sense. So, yesterday in class, we talked about, hey, here's our normal distribution. That's cute, Mr. Grom. That's so nice, and so forth and so on. And we know that if you go over to Z equals negative 1.96 and Z equals positive 1.96, between them you get 95% of the data. Okay? That's with the Z-score. Right? But Groom, I only want a 90% confidence interval. Okay, cool. Now, back in my day, we had to memorize this. I think it's easy, but if you don't get how it's easy, I'm going to show you how you can figure it out in the computer in a minute, okay? That's 90%. This is Z equals that, and Z equals this. Hey, is it always going to be symmetric? Yeah. Could we get a 99% confidence? No, theoretically, you could make one, but it's dumb. We just don't normally do that, okay? Now, the game is thus. Could you make a 60% confidence interval? Yeah, I guess, weirdo, but I would like to be confident, not, flip a coin. You with me? So here's the game. I'm going to start with this one up here. If I'm putting 0.025 in that lower tail, and I pull up my giggle sheets, Somewhere I've got a Google sheet. Oh, nope. Nope. Where's my other account? Ah! Oh, of course. Bro, it's always something, I'm telling you. Oh, for crying in the mud. One moment, please. Well, today would be handy if you'd hurry up and get to it, bro. Yeah, sign me in, bro. All right. Now I gotta go on my phone. But we're not supposed to use phones, bro. Oh, yeah, tell me about it, pal. Tell me about it. Done. Got it. Hey, all right. Let's go to Giggle Sheets. Anywho, as I was saying, you go to Google Sheets. No, stupid. Can I just have Google Sheets, please? Thank you. And so what we're going to do, of course, is we are going to go in and we are going to go into here, I guess. And we're going to go like equals norm dot s dot inverse 0.025. Boom! Negative 1.96. It's like I know what I'm talking about. What if you want 90%? Well, then you'd be doing you'd be doing 0.05 in a lower tail. And there you go, 1.645. Okay, yay! That's where those numbers come from. Will it be those numbers every time? For a Z, yes. For a Z, yes. Okay. So we're going to do a couple of those, and then we're going to, well, what happens, okay. So here's the first thing. Okay, we're off to the races. We're like, oh, this is cool. Yeah, it's easy. I can do this all day long if I wanted to. Okay, cool. So then the game is such that you're like, oh, okay. Graham, I need to know something about the average screen time. St. Helens High School senior girl. All right, so what do you do? Well, you're going to go sample some. So you sample 40 of them, sure. 40 girls, senior girls, obviously. You better be seniors. That's what we're talking about, right? And you find that X bar is, this is in minutes, 270 minutes a day. Awesome. And you find that the standard deviation is 31 minutes. Because some people, like Warlets, maybe don't ever get on their phone. Other people never get off of it. Freaking DA, put your phone away right now. Put it away. Come on now. Anyway, so at this point, you're like, yeah. So here's the game. I want a 95% confidence interval for mu, which mu, again, is the true mean. Well, I don't know, but I know it's going to be 270. That's in the middle, plus or minus 1.96. Always 31 over the square root of 40, babe. It's that easy. Bam! 9.6. So I am 95% confident that the true mean lies somewhere between 279.6 on the upper end and 260.4 on the lower end. Yay, because I minused, obviously. That's it. And so we talked about that yesterday. Presumably I did a bunch of those yesterday. That's for those of you that were gone. Ta-da. Now, what happens? What happens if I can't get a big enough sample? And so we introduce a new distribution. It's called the t-distribution. And the t-distribution, again, is very similar to the z, except it expands and contracts as n gets bigger or smaller. So as n gets bigger, this thing tends to do more like this, and it approaches, t approaches z. They become very similar. Now, what the big kids say is that when n is bigger than or equal to 30, you should use a z distribution. Okay? If z is less than 30, or sorry, if n is less than 30, you use t. Okay. What does that mean? Well, it says this. Again, as n gets smaller, this thing gets fatter. Why is that? Well, because again, I know that with a smaller sample size, there's going to be more variability. We've talked about this quite a bit. I'll just mention it again. You go sample 5 people. This is the average height of males in America. It's 5'7". Well, how did you do it? Well, I sampled 5 people. Well, Mr. Groom, I mean, I feel like that's weird. It is weird because I sampled 5 people, yeah. If I sampled 100 people, there's less variability. In fact, there's no chance. There's no chance I sample 100 random adults in America. There's no chance that I got the average is 5'5". With 5 people, there is. With 5 people, the average could be 6'2". But with 100 people, there's no chance of that because there's no variability in a giant sample like that. Does that make sense? And the bigger the sample, the less variable it is. That means that if you take a small, like again, you don't know this guy. You don't know. You can't know him. So what do you, because you're not God, by the way. That's why. Okay. So you find X bar. Oh, thunk. All right. Well, how sure are you of where you're at? Well, I'm 95%. Well, you can't be 95% confident because there's so much variability unless you go way out there, make your target wider. Now, in terms of how it works, dude, it's literally the same. The math is exactly the same. Except that, I will say this, you're never going to know SX. You're never going to know sigma, rather, ever, if you're using such a small distribution. It's a situation where you're never going to know sigma. So there's always SX up there. The only real difference, though, is T. T is a number, okay? It's a number of standard deviations, yes? And then this, of course, is your standard deviation. Well, what does that mean? It means that T is always going to be bigger than Z. And because T is bigger than Z, instead of using like 1.96, we might be using 2.2. What does that do? It pushes this out further, effectively making my target wider so I can be just as confident. Why? Because I know I'm not as confident going in initially because there's more variability in my sample. Yes, that's the game. Something else to think about is N. What is happening to N here? N is smaller, so this guy is bigger. As N gets bigger, then the whole thing gets smaller, yes? So this works in harmony. T is always going to be bigger than Z. So this by here is always bigger, this part here. And then this, because N is small, that's also bigger. What does that do? It forces my margin of error to be a bigger margin of error. And it has to be for me to be just as sure, because again, more variability in a small sample size. Now, in terms of how it's done, piece of cake, babe. Piece of cake. So again, you want to know something about the average length of daddy long leg legs. Huh? Nice. And so you sample, I don't know, I guess let's do 4 spiders. You sampled 2 spiders. Well, let's do daddy long leg back legs. Yeah. So you sampled 20, well, not 20, because they have 2 back legs. You sampled 10 spiders, which means, of course, you're getting 20 legs, right? So we're going to do 20 legs. Okay, that's what we're going with there. Okay, that's the idea. Makes sense? And so there it is. I'll try to make it harder than it is, I guess. 2.1 centimeters. They are long. That is your X bar. Your standard deviation is 0.21 centimeter. Sure, why not? And yeah, that one a 95% confidence interval for mu. So again, here's a game. We're putting 95% in the middle. That's 0.025 down here. You're like, Groom, we're going to use inverse normal. Nah, not so fast, bruh. We're going to go equals T dot inverse. 0.025, because that's half of 5%, right? Comma, now my degrees of freedom, there was 20 legs, so 19 degrees of freedom. So you notice that's basically 2.1, right? Which is weird. Groom, are you being like weird because everything's 2.1? No, that's literally by accident. I'm sorry. Okay. But I'm going to say negative 2.09. But a minute ago, when we did a z distribution, it was 1.96. I know. No, I know, right? No, I know, right? So instead of going out just under 2 deviations, we're going out just a hair over 2 deviations. Now, as far as how the math works, 2.1 plus or minus 2.09, and then 0.21 over the square root of 20. Again, had there been 200 spider legs, why, this number here would have been square root of 200. And then, so this whole number would have been smaller. And this would have been 1.96 if we'd had 200 legs. You with me? But because we only had 20 legs, this number here is bigger than 1.96. This number is smaller, so this is also bigger, meaning the entire confidence interval has gotten quite a bit bigger. Why does that tell me? It tells me I'm less confident because, obviously, we did a smaller sample size. 0.098, 0.098. I'm just going to call it 0.1. Just for the sake of argument, I can do it in my head. If that works for you, I don't really care if it does or doesn't. We're going to go with it anyways. So mu is between there, and I am 95% confident of that. Okay? All right, cool. Let's do another one. Yes, you're going to go to dairy delay. Yes, the average patty weight at Dairy Delish. Okay. But you don't have a lot of money. Okay. So you're going to sample 10 burgers. All right. You lazy butt. Lazy, cheap so-and-so. I don't blame you, though. All right. There you are. So you take it, you buy it. I want a single patty there. Okay, great. And then when it comes out, you scrape all the stuff off, and then you weigh the patty. That seems weird, but I would just eat it. But whatever, you do you. Okay. We find that the average weight is 0.2 ounce. 0.2. Come on, Jay. 0.2 pounds, but let's say 3.1 pound, or God dang, 3.1 ounces. That'd be a big burger, bro. SX 0.9 ounces. Boy, they need to get their quality control under control, dog. And I want a 90% confidence interval for, obviously, my guy mu. 90%. That puts 5% down here. Are you with me? So into the computer, and we go equals. Oh, poop. What just happened? Oh, no. Oh, no. T dot inverse. Nice. 0.05, comma. Degrees of freedom is always one less than our sample size. Our sample size was 10, so 9 degrees of freedom. Holy buckets, 1.8. Now, Groom, shouldn't it have been like 1.645? Oh, look, you paid attention to me. Yes, had we done a 90% confidence interval on a large sample size that is bigger than or equal to 30, yeah, we would use 1.645. But we didn't. We have to get a bigger thing. So here it is, TSX square root of n, 3.1 plus or minus 1.83.9 over the square root of 10. So again, I find my margin of error first. 1.83 times 0.9 divided by the square root of 10. And I get about 0.52. Holy buckets. Plus or minus half an ounce. That's redonkulous, bro. Get your quality control. You're losing money, dog. That's terrible. 3.1 minus 0.52. Good criminy. Try again. 3.1 minus 0.52. 2.58 ounces. Boy, this poor guy got screwed. You got paid how much for a burger? You got 2.5 ounces? Oh, jeez. Brutal, dog. Brutal. Okay? Yeah, we can play this game all day long. We're going to do another one. Because I care about you. You're great kids. Well, you're nice people. Well, I mean, some of you are. I mean, some of you are, some of you aren't. Whatever, I guess it's fine. Here we go. Yeah. So you want to know something about the average length of hair donated for wigs or what have you? Okay, cool. But you're lazy and you don't have time to sit around and wait. So you call and you get like 18. So 18 people donated their hair today, and that's all you had time to wait. You don't have time to collect any real data because you're lazy. Now remember, we talked about this. There's a reason why sometimes we can't get as big a sample size as we want. I think the classic one of my favorite ones is the rare Siberian tiger. We think he's rare. I think he's becoming extinct because we're a little short on sperm count. There's only one way to check that. Okay, so we have to go to Siberia, which is a fairly large, inhospitable place. I have to like fly around on a helicopter and shoot one of these things with a tranquilizer and hope he stays down while I go down there and collect a specimen. This is going to cost a lot of money. It's going to be very dangerous. And I think as a researcher, you're going to be happy if I can get 10. Well, I think you're just going to get 10 because I don't think I can afford to do any more of that. It's dangerous. It's just awful. There's only one way to find that out. And it's terrible. And I'm not going to do it any more than that. Okay, I'd like 10,000 of them. If there was 10,000 Siberian tigers, they wouldn't be They wouldn't be going extinct, would they? No, they would not. Okay, this freaking average length of hair cut in the world or whatever. I feel like a guy could get more than 18. Without like it's like falling off a bike. You get more than that. But you're lazy. You went with 18. I'm just gonna go with it. That's what you told me. And 10.7 inches. That is the average. Standard deviation of 2.7 inches. I don't know why you need any shorter hair than that, but whatever. Okay, good for you. And we want a 90% confidence interval for mute. Okay. So I can start the process. I know it's going to be plus or minus 2.7 over the square root of 18. I just don't know how many deviations I have. So into Excel I go, or giggle sheets as it were, equals T dot, oh, you dirty hippie. Give it to me, bro. T equals T dot inverse. There you go, babe. And I said 90%, so 0.05, comma, forgot what I said. 17 degrees of freedom because n is 18. And so you see it's 1.74. Once again, bigger than 1.645, which is what it would have been had we been doing a z distribution. Okay? As I promised, t always bigger than z. Always, always. Always, always. 1.1. So it's going to be 11.8 on the top end. On the bottom end, when you minus, you get 9.6. Ta-da! That's it, my man. That's all there is to it. All right, so today, again, just looking at the difference between the two of them. Okay, a little bit. Knowing when to use which. Tomorrow, we're going to get into proportions. And we'll make confidence intervals for proportions as well. Okay? And same principle. I want to know something. I don't know. I take a sample. I make a confidence interval around what I saw. Okay? All right. Bye.